In this screencast, we're going to take a look at some notes on electric circuits, key terms, and something called Ohm's law and how that applies to different configurations of circuits called series and parallel. So if you find a spot in your workbook where it has some of these key terms, you can write down these notes. Electric current we're going to define as the flow of electric charge, and that transports energy from one place to another in a circuit. The symbol for electric current is a capital I, and the unit is amperes, or what we call amps, which is abbreviated with a capital A. Electrical resistance has to do with a material which resists the flow of electric current through it. The symbol for electrical resistance is a capital R, and the units are going to be ohms, which is this Greek symbol omega. And so you can think about it as even like the wires in a circuit. They have all of these atoms and things that are represented by these little dots. If there are more things for the electric charges to bump into, more atoms, then we would say that that material has a very high electrical resistance. It's harder for the electric charges to move. If it's something like this on the bottom, where there aren't as many things in the way for the electric charges to move through, we would say that has a lower electrical resistance. Voltage, we won't go into too much detail about how this works, but we're going to define it as the potential difference in a circuit. Usually this is a battery source for our direct current circuits. We're going to symbolize it with the letter V, and the unit is also a capital letter V called volts. So electrical power is the rate at which electric energy is transferred. So it's a capital P, but the units are something that you've probably heard of before, watts with a capital W. And so this is where we get those watt ratings for our light bulbs in our homes. That's actually a power rating. One way that we can calculate power is by taking the electric current and multiplying it by the voltage V. So Ohm's law is going to give us a relationship between current, voltage, and resistance. So it states that the amount of current is directly proportional to voltage and inversely proportional to resistance. So you'll see it written multiple ways, but the best way I think to think about it is this one here, where you have the electric current I is directly related to voltage. So that means if you have more batteries, more voltage in your circuit, you'll have more current, and the bulbs will typically be brighter. But it's inversely related to resistance. So that means that if there's a higher resistance, then you'll actually have a lower current. It's more difficult for those electric charges to move. But if you have a lower resistance, you'll have a higher current. So one way that we can look at this is in a simulation from the Physics Education Technology website, which looks at Ohm's law. So this one actually works in HTML5, so it works on devices like iPads. But you can see here we have a relationship for Ohm's law, V equals I times R. And what you can do is you can use these little levers to change the values. And so one thing that you'll notice is if you increase the voltage, if you add more batteries, what happens is that the the electric current also increases, and that's represented by these arrows. So if you increase the voltage, you also increase the current in the circuit, and we're keeping the electrical resistance the same here. So I'm going to reset that. Another thing you can do is you can manipulate the resistance and see how that affects the current. So if you increase the electrical resistance, you'll notice there's more and more dots happening in that little wire there. What happens is the electric current decreases, and because it's more difficult for those charges to move. If you decrease the electrical resistance, you'll notice that the current gets larger. So if you have a low electrical resistance, that makes the current larger. So that's one way to represent Ohm's law and play around with that. Alright, so what is the main difference between a series circuit and a parallel circuit? And we'll be building some of these in class. In a series circuit, we define it as a circuit where there's only one path for the electricity to follow. So these are a bunch of different ways that you could draw a series circuit. Here we have a battery and two light bulbs in series, so they're all along the same path. There's only one pathway there. This one, you have three light bulbs in series with each other, and they're all on the same path with the battery. And it doesn't matter where you put that battery, so whether it's on the sides, on the main part here, there's only one path so that the electric current has to follow that path. So a parallel circuit, there's going to be multiple paths. So anytime you have a circuit and you're kind of looking at electric charges coming from the battery, if it gets to a point where it has a choice which direction it can follow, we're going to call that a junction in the circuit. That indicates that you have a parallel circuit. So here it could follow this pathway or it could follow this pathway. The current this here could follow this pathway or this pathway or this pathway. So a bunch of different ways that you can see parallel circuits. So I wanted to tell you a little bit more detail about series and parallel circuits, and you do have an equation sheet in your workbook where you can look at some of this information. We'll be using this to solve some problems in class, but I wanted to give you a sense of it before we do that. So in a series circuit, when you add more and more bulbs, you're going to increase the total resistance. It's harder for those electric charges to flow through the circuit, and if you wanted to calculate what that total resistance is in a series circuit, you just add up the individual resistances of each of the devices, like light bulbs or motors. And from Ohm's law, if you are increasing the resistance, what's going to happen is that your total current is going to decrease, which typically means that devices are slower or dimmer. Here's an example. If you have two light bulbs in series with each other, let's just say one has a resistance of 1 ohm and one has a resistance of 2 ohms. If you wanted to calculate the total resistance, you would just add them up, and 1 plus 2 gives you 3 ohms. And so you can see that the total resistance is higher than the individual resistances. If you add another bulb, a 4 ohm bulb, to those two that are already there, you can see that then you get an even higher resistance, a 7 ohm resistance. And since all of them are on the same path, they have the same current going through them, that total current would be even smaller in this case, and the bulbs would get even dimmer. In a parallel circuit, we're going to follow some different rules. So as you add more bulbs in parallel, what happens is the total resistance actually decreases in the circuit. And so if you have a decrease in the resistance here, you're going to get a higher total current. But that total current then has a choice. When it gets to a junction in a circuit, it's going to split, and it follows the rule that more current follows a path of lower resistance. So if you wanted to calculate the total resistance in a parallel circuit, you're going to have to add the inverses of the individual resistances, and then that gives you 1 over R total. So let's look at an example for this. If you have a 2 ohm bulb connected to a 3 ohm bulb in parallel, and you wanted to calculate the total resistance, you would do 1 over 3 plus 1 over 2, but that's adding fractions. So we're going to have to find a common denominator, and a common denominator between 3 and 2 is 6. So 3 goes into 6 twice, and 2 goes in there 3 times, so you are adding 2 over 6 plus 3 over 6, and then you can add up the numerators and keep the denominators, so you have 5 over 6 ohms. But we're not quite done yet. That is giving us 1 over R total. And so if you wanted to figure out what R total is, you can either cross multiply and you get 6 ohms is equal to 5 times R, and then you can divide it out, or you can just take the reciprocal or the inverse of this and you get 6 ohms divided by 5, which is 1.2 ohms. And there you can see that the overall or total resistance is actually smaller than the individual resistances of 2 ohms and 3 ohms in this case. Alright, so we're going to do some example problems in class, and you can see those in your workbook, but if you skip ahead a couple of pages, you see some information about light bulbs that have different wattages. And so a higher watt bulb actually has a thicker filament and a lower resistance. So it's easier for those charges to go through, and that's why it makes it brighter. But a lower watt bulb has a thinner filament and a higher resistance. And this information is on your equation sheet, but let's just take a look at some of these questions. So if we have this configuration, we have a 40 watt bulb in parallel with a 60 watt bulb, the one that has the thickest filament is going to be the one that has the lower the higher wattage and the lower resistance. So here that's going to be the 60 watt bulb. The one that has the highest resistance is going to be the one that's the lower watt bulb with the thinner filament. So in this case it's the 40 watt bulb. So then we can think about, is more current following this pathway, or is more going this pathway? So remember that more current follows a path of lower resistance, and in this case that's the higher watt bulb because it has a thicker filament and a lower resistance. So in parallel, which one's going to be brighter is going to be the 60 watt bulb, and that's what we're used to seeing in our everyday experiences in our homes. Things are wired in parallel, and so a higher watt bulb in parallel is going to be brighter, and it's got more current following that path of lower resistance. When you have light bulbs in series with each other, you're going to get a little slightly different situation. So let's say we have a 40 watt bulb and a 60 watt bulb in series with each other. The one that has the thinner filament is the 40 watt bulb, and the one that has the lower resistance is the 60 watt bulb. But since they're in series with each other, the same current is going through both of them. They're on the same pathway, so the movement of the charges is the same through both of them. But the one that's going to be brighter is going to change. So in this case, the lower watt bulb, or the 40 watt bulb, I know it's counterintuitive, is actually going to be brighter than the 60 watt bulb in series with each other. So more current is getting squeezed through that thin filament, or I guess the same current from that circuit is getting squeezed through the thinner filament, which is going to make it actually glow brighter. And I can illustrate this using a simulation. There's a circuit construction kit on the PHET simulation website where you can actually build different circuits and kind of see the movement of the charges going through them. And so I've already started building this one. This one only runs in Java, I think, so far. You can just take different wires and with different connection points and different light bulbs, and you can connect up your own kind of circuit here, and then you can right click on it and change the resistance values. And so what I did is I have a higher resistance one, which is going to be like our lower watt bulb, like our 40 watt bulb, and I have a lower resistance one, which is actually like our higher watt bulb, the 60 watt bulb. And if I connect these up, what you'll see is all the charges start moving simultaneously in those wires, and the one that had the higher resistance glows brighter. So in this case, the 40 watt bulb is actually glowing brighter than the 60 watt bulb. All right, and then that's something that you can play with on your own time, and we'll be looking at some more applications and examples in class.